Welcome, everyone. This presentation will cover the theory and practical application of cointegration testing with a focus on using the EViews software. We will explore the concept of dynamic equilibrium between variables, which is the core idea behind cointegration. Imagine a person walking a dog on a leash. Both the person and the dog might wander around, but they won't drift infinitely far apart because the leash keeps them together. This leash is like the cointegrating relationship. So, why is this concept of staying together so crucial in econometrics? Let's delve into the risks of ignoring it. This slide explains why understanding cointegration is crucial in time series analysis. The primary risk of working with non-stationary time series is spurious regression. This occurs when you find a high R-squared and seemingly significant statistical results between two variables that, in reality, have no causal or meaningful relationship. They simply happen to be trending together over time. The graph on the left, labeled the risk, spurious regression, illustrates this with two series that appear to move together, leading to high R-squared, no relationship. Cointegration provides the solution. It indicates a genuine long-run equilibrium between non-stationary variables. As shown in the solution, cointegration, graph on the right, while the variables may wander in the short term, they do not drift infinitely far apart. They are fundamentally linked and maintain a stable relationship over the long run. The context for this could be relationships like income and consumption, or purchasing power parity, where variables might move together over time. To clarify these concepts, let's define some key terms. Stationarity, IF0. This refers to a time series where the statistical properties like mean and variance remain constant over time. Non-stationarity, IF1. This describes a series that has a stochastic trend, meaning its mean and variance change and grow over time. Most economic time series fall into this category. Cointegration. This is a powerful concept where a linear combination of two or more non-stationary I-of-1 variables results in a stationary I-of-0 series. This stationary combination represents their long-run equilibrium relationship. This slide outlines the comprehensive decision framework and workflow for cointegration testing. We begin by asking a fundamental question: do variables have unit roots? This is assessed using tests like the Augmented Dickey-Fuller, or ADF, or Phillips-Perrin, PP tests. If the variables are found to be stationary, meaning they are I0, then standard ordinary least squares, or OLS, or vector autoregression, or VECM, models can be directly applied. However, if the variables are non-stationary, specifically I1, then we must proceed to test for cointegration. This crucial step helps us avoid spurious regression. For cointegration testing, we have different approaches depending on the nature of our data. If we are dealing with a single equation, the Engle-Granger or Phillips-Ouliaris tests are appropriate. For a system or multivariate of variables, the powerful Johansen test is the preferred method, as highlighted in the flowchart. For panel data, specialized tests like Pedroni, Cow, or Fisher are used. The outcome of the cointegration test dictates our next step. If cointegration is found, we then estimate a vector error correction model, or VEC, which can capture both short-run dynamics and the long-run equilibrium relationship. If there is no cointegration, we must estimate a VECM indifferences, meaning we difference the variables to achieve stationarity before modeling. The workflow steps on the right summarize this process. Step 1 is to confirm non-stationarity. Step 2 is to choose the appropriate test, whether single or system. Step 3 is to select the correct model, VEC or VECM. A critical tip to remember is to never skip the unit root test, as cointegration analysis fundamentally requires I1 series for its validity. The Johansen test is a likelihood ratio test used to determine the number of cointegrating relationships in a vector autoregression, or VAR, model. It's a powerful tool because it treats all variables as endogenous and can identify multiple cointegrating vectors, making it superior to the Engle-Granger method for systems with more than two variables. The core of the test revolves around the concept of rank, denoted as R. The rank of the matrix pi indicates the number of cointegrating relationships. If R equals 0, there's no cointegration among the variables. If R equals n, the number of variables, it implies all variables are stationary, which contradicts our usual I1 assumption for cointegration. The most interesting case is when R is greater than 0 but less than n, signifying that there are R cointegrating relationships, or stationary linear combinations. To assess this rank, the Johansen methodology employs two main test statistics, the trace statistic and the max eigenvalue statistic. Both are used to test the null hypothesis of R cointegrating vectors against an alternative hypothesis, with the trace statistic typically testing against n and the max eigenvalue against R plus 1. This slide outlines the critical assumptions regarding deterministic components when conducting cointegration tests. We have 5 deterministic trend cases to consider. Case 1, no intercept, no trend, is rarely used. Case 2, intercept in CE only, is for data with no trend. Case 3, intercept in CE and VAR, is the most common default for most economic data. Case 4, intercept and trend in CE, is used if the data has a clear linear trend, such as GDP. Lastly, Case 5, quadratic trend, is also rare. It's crucial to correctly specify these trends, as an incorrect specification can bias the rank test. Additionally, the lag length significantly impacts results, so always use AIC/SIC on the underlying VAR to select optimal lags before performing the cointegration test. This slide outlines various cointegration approaches beyond the Johansen test, each with its own advantages and suitable applications. First, we have the single equation Engle-Granger method. This is a residual-based approach, where you first run an ordinary least squares, or OLS, regression. Then you test if the residuals from that regression are stationary. Its main pro is its simplicity. However, its cons include the inability to detect multiple cointegrating vectors and its sensitivity to the ordering of variables in the regression. Next, we look at panel cointegration methods, which are designed for datasets with multiple cross-sections over time. The Padroni and Cow tests extend the Engle-Granger approach to panel data by pooling statistics across cross-sections. The Fisher test, on the other hand, combines the p-values from individual Johansen tests for each cross-section, providing a robust overall panel result. The right side of the slide provides a clear guide on when to use each approach. The single equation method is best suited for simple bivariate analysis, where you're looking for one cointegrating relationship between two variables. Panel methods are appropriate when your N, or number of cross-sections, is large, such as analyzing GDP growth across 20 different countries. Finally, the system approach, exemplified by the Johansen test, remains the gold standard for multivariate time series analysis, where you have more than 2 variables and potentially multiple cointegrating relationships. This allows for a more comprehensive understanding of complex economic systems. This slide transitions us to the practical application of cointegration testing within EViews. We'll look at how to set up your data for analysis. The image illustrates 2 primary ways to open your selected variables in EViews. First, you can select multiple variables, right-click, and choose Open as Group. The group object is often the quickest way to initially examine your raw data, and from here you can directly access the Cointegration Test option. Alternatively, you can open your variables as a var object. This is particularly useful if you're already intending to build a vector autoregression model. Similar to the group object, the var object also provides a cointegration test function. A crucial tip for best practice is to always open your data as a group first. This allows you to visually inspect correlations between the variables before diving into formal testing, which can provide valuable insights. For those who prefer the command line, EViews offers convenient shortcuts. For group objects, you can use coint method lags to run a cointegration test. For var objects, you would use varname.coint. These shortcuts streamline the testing process once you're familiar with the syntax. This slide provides a visual guide to the Johansen Cointegration Test dialog box in EViews, highlighting the critical settings to configure. First, for the trend assumption, you must select the appropriate deterministic trend assumption. The instructions advise selecting intercept no trend in CE, which is case SPRI, or allow for linear deterministic trend, which corresponds to case 4, depending on your data characteristics. Second, you can specify any dummy variables in the exogenous variables field if your model requires them. Third, under lag pairs differentialed, you enter the lag intervals for the differential terms. For instance, entering 1, 4 means you are including lags 1 through 4 of the first differences. A crucial warning here is that the lag input refers specifically to the differential terms, and entering 1, 2 in this box would correspond to a VAR3 in levels. Lastly, if you are unsure about the best deterministic assumption, you have the summary option to summarize all 5 sets of assumptions for a comprehensive overview of the results under each case. This slide presents a case study on purchasing power parity, or PPP, focusing on the relationship between price levels and exchange rates for the UK and US. The objective is to test the purchasing power parity between the UK and US. A critical prerequisite, confirmed by an augmented Dickey-Fuller (ADF) unit root test, is that all series are integrated of order 1, or I1. For data checks, we need to ensure the data is log transformed, which allows for interpretation as elasticity. We also need to check for seasonality and confirm that all series are integrated of the same order, usually I1. This slide outlines the practical steps and parameter choices for executing the Johansen Cointegration Test in EViews. First, we define the variables for our test, which are a group consisting of the log-transformed UK CPI, US CPI, and the exchange rate. We're explicitly assuming these variables have non-zero means, hence an intercept is crucial. In the EViews dialog box, under Deterministic Trend Assumption of Test, we select Option 2, Intercept No Trend in CE and Test VAR. This choice assumes that while individual series may have trends, their linear combination, which forms the cointegrating equation, removes any stochastic trend. Essentially, we expect the long-run equilibrium relationship to have an intercept, but no deterministic trend. We also include an exogenous variable, DUM, which is likely a dummy variable to account for specific events or structural changes. Finally, a critical parameter is the lag interval for the underlying VAR model, which we set from 1 to 4. This lag length choice is either based on an assumption suitable for annual data or, more robustly, derived from prior lag criteria results, ensuring the residuals are well behaved. After running the Johansen test, we get a table for the trace statistic. The key is to apply a specific decision rule. You start from the top hypothesis, which tests if there are 0 cointegrating equations, meaning R equals 0. You compare its probability value to your significance level, typically 0.05. If the probability is less than 0.05, you reject the null hypothesis. In this example, the probability for none is 0.0288, which is less than 0.05, so we reject H0, R equals 0. Then you move down to the next row, testing the null hypothesis of at most 1 cointegrating equation, or R less than 1. Here, the probability is 0.2881, which is greater than 0.05. Therefore, we fail to reject this null hypothesis. You stop at the first hypothesis you cannot reject. This hypothesis determines your cointegrating rank, R. Since we rejected the hypothesis of none, but failed to reject at most 1, we conclude that there is exactly 1 cointegrating equation, meaning our rank, R, is 1. EViews provides normalized cointegrating coefficients. The variable with the coefficient of 1.00 is the one normalized on, in this case, L exchange. A critical point to remember is the sign flip rule. EViews reports the vector beta such that beta times yt is stationary. To express the equation in the familiar form of y1 equals beta 2 times y2, you must reverse the signs of the coefficients shown in the table, except for the normalized 1.00. So, from the raw output, 1.00 times L exchange minus 1.05 times L CPI UK plus 0.98 times L CPI US equals 0. We rearrange this to get the implied long-run relationship. L exchange equals 1.05 times L CPI UK minus 0.98 times L CPI US. This interpretation suggests that the exchange rate adjusts to price differentials, aligning with economic theory. Once cointegration is confirmed, we estimate a VECM, vector error correction model. This model is powerful because it captures both short-run and long-run dynamics simultaneously. The short-run dynamics are handled by the lagged difference terms of the variables, like d of yt minus 1. The long-run dynamics are handled by the error correction term, or ECT. The ECT is simply the lagged residual from the long-run cointegrating equation. It represents the deviation from long-run equilibrium in the previous period. The coefficient on this term, often called alpha, is the speed of adjustment. It tells us how quickly the variables correct back to equilibrium. For the system to be stable, this coefficient must be negative and statistically significant. In the output, the coefficient for coineq1 in the d of SPT equation is negative 0.117. This is the speed of adjustment, alpha. It's negative and significant, indicating that when the spot rate deviates from its long-run equilibrium, it corrects about 11.7% of that deviation in the next period. Estimating the VECM is a major step, but we're not done. We must validate the model to ensure it's reliable. This slide focuses on single-equation cointegration estimation methods, particularly fully modified OLS, or FMOLS, and dynamic OLS, or DOLS. These methods are used when you have only two variables or assume a single direction of causality. The primary benefit of FMOLS and DOLS is their ability to correct for endogeneity and serial correlation, issues that standard ordinary least squares, OLS, estimation cannot adequately address. To elaborate on the differences, FMOLS employs a non-parametric correction method to handle these issues. DOLS, on the other hand, corrects for nuisance parameters by incorporating leads and lags of the differenced regressors. It's often found to perform better than FMOLS, especially in smaller sample sizes. Finding cointegration is a statistical result. We must validate the resulting VECM to ensure it's a good model. The first check is to ensure the residuals of the VECM are stationary, or I0. They should behave like white noise. We run diagnostic tests on these residuals, such as the portmanteau test for no autocorrelation and the Jark-Barra test for normality. Additionally, we check for residual heteroskedasticity. As we discussed, the error correction term must be negative and statistically significant in at least one of the equations. This confirms that there is a mechanism pulling the system back to equilibrium. Finally, and perhaps most importantly, do the signs and magnitudes of the long-run coefficients make economic sense? If the results contradict economic theory, you may need to reconsider your model specification. This slide serves as a quick command line reference for various econometric tasks, particularly useful when performing cointegration analysis in EViews. First, to open a group of series, you'd use the group command, followed by the group name and the series names. For example, group G1, series 1, series 2, series 3. To conduct a Johansen cointegration test on a group, the syntax is g1.coint s,2 at trend. The .coin suffix is the primary method for groups. The s,2 indicates a summary of all trend cases, assuming a lag of 2, and at trend specifies the deterministic trend assumption. For a single equation cointegration test, like the Engle-Granger method, the command is g1.coint method equals eg. When it's time to estimate a vector error correction model, or VEC, you'd use var v1.ec c,1, 1, 2, series 1, series 2. The EC command is specifically used to specify a VEC model within a var object. Lastly, for panel cointegration tests, such as Pedroni, the command is p1.coint method equals Pedroni. This section provides a list of suggested readings and resources for further understanding of cointegration testing. The suggested readings include seminal works such as Cointegration and Error Correction, Representation, Estimation, and Testing by Engle, R.F., Engle-Granger, CWJ, 1987. Likelihood-Based Inference in Cointegrated Vector Autoregressive Models by Johansen, S., 1995, and Numerical Distribution Functions by McKinnon, Haug, and McKillis, 1999. Additionally, it recommends the EViews 13 Users Guide 2, chapter on Cointegration Testing. For general resources, users can refer to the EViews Help System, F1, the Viet-Lod Economics Group, and original papers for advanced theoretical understanding.